This video is to help you understand the fundamental theorem of algebra. We've been studying about polynomials, and polynomials, remember, have zeros, and the fundamental theorem of algebra basically deals with those zeros. It says that whatever degree your polynomial may be, so any nth degree polynomial, has exactly n complex zeros. Now that may mean you see them on the graph if they're real zeros. It also may mean you get some imaginary zeros. And the way to determine whether or not they're real or they're imaginary deals with, again, whether you see them on that graph. Now, because imaginary zeros always come in pairs, as we probably remember from quadratics, when you got one imaginary answer, you always got two, because you might have had something like a parabola like this, or if it didn't cross at all, you got two complex zeros. Also with parabolas, we found out that we normally had two real zeros, but you could also get one zero. And what we call that is a repeated zero. Why do some functions not seem to follow that fundamental theorem, where if it's to the second power, we always get two zeros? Well, because they could also have repeated zeros or complex zeros. Again, complex zeros being imaginary, where they don't show up on the graph, and repeated zeros being where it just bounces directly off that axis. Linear functions, notice x to the first, of course, always only cross once, but it's when it starts to get these curves that we start to have those problems. Really quick, just to review, again, solutions to an equation are also called zeros. When y equals 0, we're trying to find x. There can also be called roots of an equation, or x-intercepts, again, if they're real. Now, when we get to larger polynomials, that same idea happens. So if I see a cubic, such as in the upper left here in the orange, when I see x to the third, I expect to see three zeros. But you'll notice here, we only see one right here and one right here. But again, talking about that bouncing zero, when they bounce off the axis like that, we call this a double zero. So therefore, we actually are seeing three zeros. This single over here at the left, and then two zeros on the right. So I see three zeros, right? One single and one double, in order to account for the fact that I technically get all three of those zeros. Over here, I do see all three places where it's just straight crossing that x-axis. So again, we got three real zeros on that one. But over here at the right, now you'll notice that it started to curve down but never quite reached that axis. So I only see one real zero. And I don't see any doubles or triples or anything happening other than that. I don't see any bouncing or anywhere where it curves through the axis but crosses through. Therefore, I would imagine that there are two complex zeros. Again, they always come in pairs, so if there's one complex zero, there's always two of them. And we could check that out using either polyroots on our calculator or dividing out that one real zero and finding the other zeros, which we'll talk about in just a minute. Now, down here, again, we're seeing fourth power. So again, a couple of different things we could see. We can see four real zeros here. Or over here on the right, we see two real zeros. And I don't see any bouncing zeros. Again, we see that curve come up, but it doesn't hit the axis and bounce off. So there must have been two real, and again, two imaginary or two complex, right? Typically, we're calling them imaginary zeros down here at the bottom. Now, the next thing we would do with this, the reason we need that fundamental theorem, is so that we can find all zeros of a function. And the best thing to do if you want to find all zeros is graph right away. So go ahead and type f of x equals x cubed plus 5x squared minus 4x minus 20 into your calculator and see what picture you get. I'll do the same thing in just a second. All right, so if I go to my calculator and I type that in, you'll notice we get a screen where it's crossing through the axis. We can't see the maximums and the minimums, the high points and the low points of the curve. But remember, we're just looking for zeros. Where are we crossing that axis? So if I grab that picture, we'll notice that we see three places that we cross that axis. So I'm going to take a quick snapshot here of that function. I'm going to jump back over here, and we see those three places on our graph. It looks to be at -2 right here. Make -3, 4, this is -5, and over here at 2 as well. Well, because I only expect three zeros, I can say that my zeros of my function were -5, -2, and 2. And a great thing to do with those, by the way, just because graphs can be deceiving, is while we still have that calculator open, we could always check the table if you think they're nice whole number answers. So just press Control T or go to the menu and open up your table, and we can double check and see. Let's go up a little bit here. I'm just going to arrow up to -5, 0. Notice we had -2, 0, and we also noticed at 2, 0, and we verified that those three places definitely had zeros. Now, if we type our other function in, so we go back to our graph here, go ahead and take a second, type that one in your calculator, and let's see what you see there. All right, on my calculator, you'll notice, and I've got the other one typed in down here, I'll just turn off F1, turn on F2, and then close it down with my arrows on the right again. You'll notice that I only see two places that seem to cross that x-axis. So again, I'm thinking, well, I've got two real zeros, and they look to be at -2 and 1. So on my page, I might at least note, okay, it looks like I'm crossing at -2, and then coming back up at 1 over here. So that's where I get at least two of my zeros. But how am I supposed to find my other two? Again, if I'm missing a pair of them, my guess is they're probably imaginary. They're probably complex zeros. So let's think back to division. If I know some of my zeros, I can divide them away using synthetic division and find what's left over. So I'm going to go ahead and do that very quickly. Oops, adding there. Multiply by 1 again is 2. Add them up. Makes 4. Add them up. Makes 0. And then take my second 0, because now I'm down, instead of being x to the 4th, we're at x to the 3rd. I can take that other 0 out of there as well. So I can drop that one. Makes -2, 0, 0 is 4, and that's -8, and it disappears. And notice we're left with what used to be x to the 4th, then became x squared, or sorry, x cubed, is now x squared, plus 0x plus 4. And I can try to find out where those zeros are. X squared would be equal to -4, and therefore take the square root, and you'll find out x equals, the square root of 4 is 2. We got to say plus or minus, but notice it was -4, so we got imaginary. And plus or minus 2i, positive 2i and negative 2i, would be my other zeros. So that's a great way, if you can find a couple of good real zeros on the graph, use those in synthetic division or long division, either one's fine, to find your other zeros. Now, sometimes those zeros don't come out quite as pretty, but your directions might be a little bit different. They might just say approximate the real zeros. Right? So what you can do, accurate to 3 decimal places, of course, remember, don't be too stingy, is go ahead and go on your calculator again and plot that graph. And you'll notice that we get a graph that kind of swoops down and swoops back up. So again, I'm just going to make a quick sketch so I know what I'm looking at. It's coming down here, and it swoops over and kind of comes back up there. But I get at least a couple of good zeros. Now, they're not quite as great as my last ones, because notice they don't seem to hit those tick marks. Or if we check the table, in between 2 and 3 here, you'll notice we went from a negative number to a positive number in the y-axis, which means I must have crossed through 0. Unfortunately, that's not a nice number. It doesn't come out as a nice round whole number. Same thing goes over between 0 and -1 here. We go from 2 to -2, which means, like we said, on our graph, we must have crossed that axis, but it's not a nice number. The nice part is, it said to approximate the zeros. So I don't really need my table. I'm going to go ahead and turn that off. What I want to do is find those zeros using my calculator. Decimals are just fine, don't have to be exact. So let's go ahead and go to Menu. We're going to analyze part of our graph, and I'm going to find zeros. Notice that first option is find the zeros. And now it's going to give me a vertical line, because it wants to know between where and where am I looking for these zeros. I can't find both at once. So I'm going to go ahead and click on the graph a little bit to the left side of one of my zeros. Now it says upper bound, so I'm going to scroll over, and you'll notice it's kind of a gray out area. Gets a little bit gray there. And if I scroll past my 0 and then click again, it'll find that 0 for me right there. So it looks like -0.732 is one of my zeros. So accurate to 3 decimal places, negative 0.732 looks to be one of my zeros. Let's go find the other one. So again, menu, analyze, 0, and again I'm just going to go to the left side of my point and then scroll it over, click again, and it looks like 2.732 is my other good answer. So that's where I got these two numbers, just a little bit past 2 and a little bit inside of negative 1. Right? So very badly drawn graph, but at least I have accurate zeros, accurate to 3 decimal places there. All right? The last thing that we're going to do with the fundamental theorem is realize that, hey, if we know that that number of zeros can determine, or my degree can determine my number of zeros, how about we go backwards? What if they give me a number of zeros and I want to write a polynomial? So write a polynomial in standard form with the real coefficients of least degree, with the given zeros, so you give my information, and a leading coefficient of 1. What that saves me is having to do any extra work. I'm not going to worry about having a leading coefficient. I'm going to leave that as a 1. But given that zeros and factors are related, I know that in my problems earlier, if I had factored them out, right, so we can scroll back here real quick, when we had these individual factors like x squared plus 4 but not broken quite down yet, the fact that we had a 1 here meant that there must have been an x minus 1 in the problem, right? That negative 2 made for an x plus 2. That must have been a factor of my problem. And even that plus or minus 2i meant that I had a minus 2i and a plus 2i in my problem. So those were the different factors that would have formed f of x. Well, if we go back here, that means if I have negative 5 as one of my zeros, I can say that x plus 5. When plugging in negative 5, it would give me 0. That's one of my factors. And we can do the same thing with my negative 2 right there and my positive 2 right here. Should probably do those in order as how they're written though. Remember that positive 2 gives you x minus 2 as a factor. Negative 2 would be x plus 2 as a factor. And now the only trick is, in order to get into standard form, we just need to do some foiling and distributing. So remember, minus 2 plus 2, those two things are going to give us x squared. Minus 2x plus 2x disappears, and a minus 4 afterward. And then if I FOIL that out, f of x will end up equal to x times x squared is x cubed. X squared times 5 is a 5x squared. Negative 4 times x is minus 4x. And my constant term is negative 20. And there is the standard form polynomial. For the next one, the same idea works. So let's go ahead and write out the first couple of factors. If we're going to have a positive 2, again, that means I need an x minus 2. The negative 2 makes for x plus 2. And when I FOIL those together, I know I'm going to get x squared minus 4, so that was kind of nice. I also have a negative 6i, so I'm going to say x plus 6i. And remember that imaginary numbers always come in pairs. So if I have a negative 6i, I also have to have its conjugate pair. Remember, that's its conjugate partner. J-U-G-A-T-E, conjugate pair. So that x minus 6i would also need to be one of my zeros. Now the nice part is, again, they're also a difference of squares. So I can say x squared, my inside positive 6i, my outside negative 6i disappear, and I can just get a nice solid negative 36i squared, but remember that just becomes plus 36. And then the final thing to do is just FOIL those together. So I get x to the 4th. You get a negative 4 and a positive 36 is going to be a positive 32x squared. And then finally, negative 4 times 36 is 144. So f of x would equal that function. I hope that helps you with polynomials. Have a great day. Ask your teacher with any questions, and good luck.